Thank you. Yeah, so I don't really directly work in large deviation problems, so I don't know. So, but I chose some topic. It's a kind of survey type talk with I'll present many results on these two. There are 2 point processes in the plane, and they are somehow similar but yet different. And so I'll present several results, including some large deviation like results of this kind. So let me start by introducing the 2 point processes, what they are. So the first one is the zeros of a random entire function. So this is what is called a Gaussian entire function. GEF is the Gaussian entire function. Of course, there are many Gaussian entire functions, but I mean this particular one. It is got like this. It's an infinite power series, an z to the n over square root of n factorial, where these coefficients ans are IID, standard complex Gaussian random variables. What that means is that the real and imaginary parts are IID normal, 0, variance half. Okay, so that's just a normalization. So this converges in the entire plane. So this defines a random entire function, and so the first point process will be just the set of zeros of this random entire function. Any holomorphic function, the zeros form a discrete set, locally finite set. So what you get is a point process. In any compact set, there are only finitely many points. Okay, so so it is useful to think of it sometimes as the limit of Fn, which are just random polynomials, just the truncation of these random polynomials. As n goes to infinity, these converge to that uniformly on compact subsets, and so zeros will converge to zeros, etc. So. Okay. So another way to say it is, here I have said it in one way, but an invariant way. What I mean is, here is the way to say it. It's just what it is a complex Gaussian process. Let's say this f of z is a complex Gaussian process in the plane, and it is centered. The expected value of f of z is always 0, and the covariance is given by this expectation of f of z, f of w conjugate, that if you do this, you will get e to the zw bar. So you may think that's the reason for the square root, which might have looked like a strange choice, but the covariance function is just exponential, and I will say more why this particular choice of coefficients. This is a particularly unique choice of coefficients, and this is the covariance function. So when you are in the complex Gaussian setting, you don't need to consider expectation f of z, f of w, that will be 0. So this is all that is required. So this is a complex Gaussian process with this covariance. That's another way to describe this random function. Okay, so and similarly, if you take this particular function, its covariance is just z to the k, w bar to the k, the truncation of the exponential function up to n terms. Okay, so this is the Gaussian entire function, and these are called Weil polynomials. These were introduced by well, in some forms they existed, but this particular form with complex Gaussian coefficients, they were introduced by Bogomolny, Bohigas, and Lebovich. And one of the key things about it is the property that I will say next, that there is some kind of a translation invariance or stationarity in this. So this point process that we get will be a stationary point process in the plane. What do we mean? So let's just look at this covariance function for a moment. So this is e to the zw bar. Okay. Suppose if you consider the covariance at z minus zeta and w minus zeta, fix some zeta, then it is e to the z minus zeta, w minus zeta bar. If you expand it, you will get e to the zw bar. That's one term. That's k of zw. Along with, okay, I actually missed some terms here. Sorry. Yeah. So there is actually. It should have been e to the zeta bar z plus zeta w bar plus mod zeta square times k of zw. That's what I should have had on the actually all the signs also. Okay, sorry about that. So this is e to the minus zeta bar z minus zeta w bar plus mod zeta square and k zw. So anyway, so what that means is, if I look at this function, the translation, you translate your function and then multiply by e to the zeta bar z. Okay, so that has the same covariance as the original function. So if you translate your function and then multiply it by this e to the zeta bar z, it has the same covariance. So this function f zeta is another complex Gaussian process, and it has the same covariance as f, so they are the same in distribution. The analytic function itself is not translation invariant. If you translate, it's not the same, but you have this deterministic holomorphic function, you just have to multiply by that and then you get this. What we are particularly interested is in the zeros, and since this exponential factor anyway doesn't have any zeros, what this tells you is that the zeros of f are translation invariant. If I take the zero set of f and the zero set of f translated by zeta, what is that? That's just the zeros of this function. The zeros of this f zeta are the same as zeros of f translated by zeta, so they have the same distribution. Okay, so this is the stationarity property of this particular Gaussian analytic function. So that's the main reason why you study. You can study any power series with Gaussian coefficients, but this is particularly nice because of this reason. Okay, so yeah, please stop me if I'm not clear or if I can explain. So this is the key point, and more or less it is the only one. There is some sense in which it is the only one actually. Okay, so I will not go into that point, but this is a unique choice almost, by which you get this translation invariant zero set. So that means the zero set, I'll show a picture of it later. So that is object number 1. So this random entire function and its zero set, which is a stationary point process on the plane. That's object 1. So I said the tale of 2 point processes. What's the second point process? It is what is called a determinantal point process. I'll explain what it is. It's the Ginibre ensemble. It is a point process in the plane. Okay, so what a point process means, just a random locally finite set. Okay, in any compact set there are finitely many points. I always think of simple point processes. So so it's just a discrete set of points. So how to describe a random infinite set? So it is done. This is very familiar to physicists by what are called correlation. These joint intensities are usually called correlation functions. So you calculate the correlation function at z1, z2, zk. It is essentially, I have made a mistake here. So so there is another typo here. So actually, what I have done is I have not normalized like this. Is actually determinant of k of zi zj times, I expressed it with respect to a different measure, but let me describe it like this. It's not exactly that, but it is this with the Gaussian measure. Okay, so the joint intensities, if I write it, if I normalize like this, then it should be multiplied by some Gaussian factors. Actually, I have expressed it with respect to Gaussian measure, that's why. So in particular, if you take k of zz times e to the minus mod z square, that's the first intensity, and that is 1. So that's the same everywhere. Okay, so in fact this point process is also stationary, and so that is seen from translating the kernel. Again, if you just translate the point process, the joint intensities are just translated, and then you can check that the determinant doesn't change and you get back the same thing. Okay, so so actually so if you normalize this is pi, it is the p1 of z is 1 over pi in the plane. So it is 1 over pi points per unit area. That's expected number of points per unit area is 1 over pi. Okay, so I just introduced this point process, but unlike so there we saw it as the zeros of a random analytic function. Actually, the finite Ginibre ensembles have such a probabilistic interpretation as the eigenvalues of a random matrix. In fact, if you take an n cross n random matrix whose entries are IID complex Gaussian, then its eigenvalues will form precisely this n-point Ginibre ensemble. In fact, that is the context in which Ginibre discovered this in 1975. So, and when you let n go to infinity, you get this other point process. But unlike in the other situation, we can't let the matrix go to infinity and say that there is an infinite matrix whose eigenvalues they are. Whereas in the case of entire functions, we could let the polynomial degree go to infinity and get a random entire function. So I can't give you a direct interpretation like that of the infinite Ginibre ensemble. Okay, so here is a picture of the two things. So this is the Ginibre ensemble, and this is the zeros of the Gaussian entire function. This is just a patch of it, and you kind of see that they look stationary in some sense, that it looks the same in different patches, they look the same. But they look very similar also, but actually there are some stark differences too between these things. Any questions? So let me start with some basic features of this kind of point process. How do we study anything about this? In case of the Ginibre ensemble, you have given all the correlation functions, so you can calculate many things with that. Whereas with the Gaussian entire function, that is not the case. You have described it as the zeros of an entire function. There are some other methods to calculate various things. But I summarize some basic results. So for example, if I look at the number of points in a disk of radius r. Let's take a disk of radius r. Let's calculate the expected number of points. Since there is 1 pi points per area, the area is pi r squared. So the expected number of points is r squared as well as. Okay, so in the case of Gaussian entire function zeros, I haven't said what is the case. It would be constant, but that constant 1 over pi. And so the expected number of zeros is actually the same for both. And for contrast, I have taken a Poisson process with the intensity 1 over pi. That also will have the same expected number of zeros. Whereas the difference comes if you see the variance. If you look at the standard deviation of the number of points in the disk of radius r, in case of Poisson, it will be like r squared. Whereas in case of these 2 point processes, it's proportional to r. The standard deviation is like square root of r. Okay, so one way to think of it is somehow the points are like almost like a lattice. If you think of a lattice and you just randomly perturb it a little bit and you count the number of points in a large disk, the deviation comes only from points which are near the boundary, which may go out or in. And that boundary has length r. So basically that is where the fluctuation comes from. So roughly they are like that. In this, you don't see the difference between these two, but there's a strong difference with the Poisson process. But more funny things happen, but these processes, although they look very similar, are very different. These two processes are very different. For that, let's not count the number of points, but let's take a linear statistic. Okay, what is a linear statistic? I fix some function, phi. Okay. And then I just scale the function and sum it at all the points. So phi of z over r, that's the sum of the values of the function at all the points. For example, if you had taken phi to be the indicator function of the disk, then when you do this, you are just counting all the points in the disk of radius r. But here we are just adding a smooth function. So I should have written here, it's a smooth function which we add at the points like this. Compactly supported smooth function, for which we scale the function and then add it at the points. So then, in case of Poisson, the variance will go like r squared times the L2 norm squared of phi. That is an easy calculation for Poisson that one can do. Whereas for the Ginibre ensemble, the variance will not even go. It will actually, even when you are covering larger and larger regions, the standard deviation just stabilizes to a constant times the gradient phi mod square. So this is again kind of understandable if you think of this as a lattice with minor perturbations. Okay, then in the case of when we are counting points, a huge difference can be caused by a point inside the disk of radius r going out. It used to contribute 1, now it contributes 0. But now that you have a smooth function, when a point moves a little, the change in the contribution is very small. And in fact, the total variance is quite small. It's just the L2 norm squared of the gradient. But it's even more strange when you look at the Gaussian entire function zeros, that the variance actually goes down to 0. It is variance will, even though you are covering larger and larger regions and adding this function at those points, the variance is actually going down to 0. It is going down like this. As okay, again, sorry for the typos. This So for the Gaussian entire function zeros, it should have been not gradient but Laplacian phi square. But with the decaying thing. So the variance actually goes down to 0 when you take our larger and larger number of points. And but in all these cases, even though variance is very small, the central limit theorem is actually true. So even though it's a very small fluctuation, there is central limit theorem for these kind of quantities. This quantity you can prove a central limit theorem when you normalize by its standard deviation, which is going to 0. So this this result about the fluctuations with not gradient square there, but that was proved by Donner, and this central limit theorem in the Ginibre case is due to Gaider and Vega, and in the Gaussian entire functions due to Sodin and Sigelson. So why this strong difference between the two kinds of point processes? So I don't know, when I have discussed with people, this is the best explanation I could kind of come up with. See, if you look at when we are thinking of a random matrix, okay, so let's say we have IID entries. If you look at IID entries, but when we think of a random polynomial, we are looking at something like z to the k over square root k factorial, k equals 0 to n. Okay, so here the eigenvalues are, let's say, lambda 1 up to lambda n. So you have all sorts of things like if this matrix is A, summation, if I take, if you take the characteristic polynomial, these are the roots. So for example, if I take summation lambda I to the power p, you will get trace of a to the power p. Here, if you look at, let's say, the elementary symmetric, so let's say the zeros are lambda 1 up to lambda n. So there are all sorts of relations. So lambda 1 up to lambda n will be a n minus 1 over root n minus 1 factorial over a n over square root n factorial. But even if you go to the product, lambda 1 up to lambda n, you will just get a naught divided by a n over square root n factorial. So in some sense, if you look at these kind of quantities, high degree polynomials, when you look at traces of the power of a matrix, you get all sorts of products of entries. Okay, when you expand it, you will get product of p entries, and then you have to sum over all combinations. When you have IID random variables and you take products, it gets wilder and wilder, very wild. Whereas in case of polynomial, even a high degree polynomials like this or the previous elementary symmetric functions, forgetting this factor is just ratio of two independent random variables. Somehow there is some global constraint which is keeping these kind of quantities well behaved in case of random polynomials. Whereas for this, they are becoming products of larger and larger number of independent random variables which are extremely ill behaved. So I think this is why the noise in the zeros of the entire random polynomials is kind of smoother compared to the noise in the determinantal process, the Ginibre ensemble. At least, okay, that's the. So here already we see some differences and similarities between these two, and this is the picture that I already showed. They look very similar, and indeed they are very similar when you look at local things. They are different when you look at, in some global sense, there are some constraints holding the zeros in place. Whereas locally they look exactly the same, and in fact the k-point correlations behave like the product of van der Waals square. That is true, but this is when you fix compact and you fix the number of points, the k correlation up to constant, same as this product square, it is the point processes. But this kind of thing is not uniform over the compact set or over the k. You take higher correlations, this breaks down, this comparison breaks down. So locally they are similar, but globally they are quite different. Okay. So, well, there are global results to show this, like this, okay. So, well, I don't know, I mean, can you see such things? I mean, you need to really love these things to see some difference between, I don't see a difference. It's like, can you see a function and see its fourth derivative or something? It's hard to see. You can see the intensity, you can see clustering, but higher, how will you see it, even the 3-point correlation? Can you see it? I don't see it. At least I don't know how to see it. Okay. So now let me come to some kind of large deviations questions. There are various large deviations questions which are kind of interesting in this regime because they are both very interesting point processes, very different from Poisson, and one can ask for all sorts of deviation questions. One is this overcrowding question which I considered a long time ago. So let us fix a disk of radius, let's say 1, and I ask what's the chance that, so what I expect is a 1 over pi times the area. That's, I mean, if take unit disk, I expect 1 point to be there. But what's the chance that I see a large number of points m inside this disk? If you are doing Poisson, then you know how it behaves. It's the tail of the Poisson random variable, which is which we understand well. But here it is not like that. It's not like e to the minus m, but e to the minus m squared log m. It's extremely unlikely compared to Poisson that you will have a large number of zeros crowding into a single in a small region. So this is true. This for Ginibre, this is a trivial calculation. Well, after one knows some facts, but for Gaussian entire functions, this is not so trivial to prove it. At least I don't know any proof that's very trivial. So I want to just give an idea, since I'm mostly going to be telling results, so I want to give an idea of how one works with this Gaussian entire function at all. So by just saying how you get, say, let's say the lower bound for this kind of probability. How can I want to say that probability to have m zeros is at least e to the minus half m squared log m. Suppose you want to say something like that. The lower bounds are easy, the upper bounds are the difficult things. Why? So to achieve that lower bound, you just have to imagine what we understand are the coefficients of this random entire function, which are independent random variables, complex Gaussian. So if you can arrange them so that you get the event that you want, then that's a lower bound for the probability of the event that you want. And when you want a lot of zeros, there is a simple way to force an analytic function to have a lot of zeros. You make the first m minus 1 coefficient 0, then you will have m zeros at the origin, because it starts with z to the m. Right? If the first m minus 1 coefficients are 0, it starts with z to the m, so there are m zeros at the origin. Of course, with random variables, you don't want to constrain them so much, but you just make the first m minus 1 coefficients very small. Okay? And then you will get, you ensure that the mth term, which is this am z to the m over m factor, square root m factorial, dominates the rest of the power series on the circle of radius r. If that is true, then by standard complex analysis results, I mean Gaussian theorem, whatever, so the number of zeros of the original entire function and this one will be the same inside the disk, and this function has m zeros at the origin. So what you need is the mth term to dominate the rest of the terms, and that can be arranged. So how do you arrange? As I said, you make the first few coefficients small, first m minus 1 coefficient small. You don't really have to worry about the large coefficients because this 1 by square root k factorial will take care of that. When k is large, this quantity is anyway small. I don't need to worry. That's going to be cheap to fix that to be small. All I want is that the first few below this m, they have to be small. Then you get the lower bound for the probability. That's the way lower bounds are obtained in this and all the results that I will mention. So, but upper bound, you have to do some bit of work to do this, get the upper bound like this. Okay. So this is one kind of large deviation where you took a fixed region and asked for an overcrowding of a large number of zeros coming into a fixed region. But you can ask other sorts of large deviation like questions. So another one, so this is, so the rest of the ones, here it is a fixed region and large number. In the next results, it will be a growing region, but still you want a deviant event. Okay? So like you take a disk of radius r, suppose. Then you expect r square many zeros there, but now I ask for the deviation from that. That I want not r square, but the deviation from r square is by a power of r, suppose. So that is that the number of zeros, let's say, is more than r square plus r to the 3 by 2, r square plus r, etc. So what kind of probabilities can we say here? So there is a very interesting phenomenon that was discovered by Yankovici, Lebowitz, and Magnificat in the case of the Ginibre ensemble. Okay, so but the same law was proved for the Gaussian entire function zeros by Nazarov, Sodin, and Wolberg. It's much harder in some sense. but the same law is true. What this is saying, if that log is a bit unclear, so what this is saying is like this, that if I want probability let's say you want n of r to be more by r square by some r to the power alpha. Now the kind of probability will depend on what this alpha is. There are two transitions in that alpha. Okay, so if you ask if alpha is bigger than 2, then if you want to read what is there, it is like e to the minus r to the 2 alpha for r bigger than for alpha bigger than or equal to 2. So this probability is like it decays like that, e to the minus r to the 2 alpha. Whereas for alpha between 1 and 2 there is a different behavior, and for alpha between half and 1 there is a different behavior. See, square root r is the standard deviation, so below alpha equals half there is no meaning to ask this question. It anyway, n of r deviates from its mean by order of square root r. So we go from half to 1, 1 to 2 and 2 onwards. And there are completely different exponents here, 2 alpha minus 1, 3 alpha minus 2 and 2 alpha. So it's this proof of this is hard to, one has to do. In case of Ginibre, it's a matter of doing some amount of calculations. In case of Gaussian entire function zeros, it's a lot of work. But the idea is that there are two kinds of change here, transition points, 1 and 2. What is 1? When we are taking the deviation goes from about r, right? When alpha is 1. When alpha is 2, you are asking for a deviation of r square. So in a disk of radius r, there are r square points. So this here, when alpha equals 2, you are asking for a kind of bulk deviation, that of the order of the volume. Whereas alpha equals 1, you are asking for a deviation which is of the size of the boundary. So those are the 2 points where the transition happens. Okay. So anyway, so I just put this result up, but I want to go further to another very specific one, namely what?
Is alpha greater than 2, does it take care of the entire?
Good. Yeah, that's exactly the next. Yeah, you're right. Alpha equal to 2 is what you are asking. So when you want, so that's exactly good. So that's exactly what I have here. The whole probability, which is that probability, let's take a specific one, that probability there are no points in the disk of radius r. R is a large number and you want no points. You can map it here, that is like its mean is r square, you have to divide by r square. Of course, it is that. But I must say here that although I wrote this is not entirely correct. Here there is a log. So in fact, there are corrections of log r here when alpha is more than 2, but that's being whitewashed. But let's, in the whole probability, I won't look at log scale, but at the log scale. So let's look at probability that there are no zeros in the disk of radius r, for example. This is an interesting quantity called whole probability. It is, in the case of Ginibre ensemble, it is a easy calculation. There is an easy calculation because, well, okay. So I don't want to explain. There is, you have the formulas. In case of the Ginibre ensemble, we have formulas and we have to work with them. It's possible to find exactly the probability that n of r equal to 0. It comes out as some product, and you can easily check that it decays like e to the minus 1/4 r to the 4, which is very interesting because for Poisson process, the probability to have no points in a disk of radius r would decay like e to the minus r square. It would be exactly e to the minus r square. Here it is like e to the minus r to the 4, exceedingly unlikely. And the same is true for the Gaussian entire function zeros. So this was shown by Sodin and Sigerson. It's an amazing paper, but they did not do the whole thing. What they showed was that this probability is between e to the minus some constant r to the 4 and above e to the minus another constant r to the 4. And there is a really two excellent papers of Alan Nishri, quite amazing. So where he managed to find this constant, not just for this, he found it in all sorts of Gaussian analytic functions. So in particular, in case of this Gaussian entire function, that constant instead of 1/4 is some 3 square by 4, whatever it is. Okay. So that is the number. Okay. So that was known. So these results are from about 2006, 2010 between them, 2003 to 2010. So this was known. So this is for a disk. If you take some arbitrary shape, suppose I take a square and ask what is the probability there are no points in that. Actually, it is quite tricky even for the Ginibre ensemble. The exact calculations don't work anymore. What was used in these exact calculations, there is kind of a spherical symmetry of the Ginibre ensemble that was helpful there. Whereas in case of if I ask what is the probability to see no points in a large square, it is hard to get the exact answer. But you can of course put a disk inside and put a disk outside, and you can get upper and lower bounds like this. If you want probability no points in a square of side length A, then it will be between some constant c to the minus constant r to the 4, because you can put a disk of radius some proportional to r inside and a disk of radius proportional to r outside. But does it decay like e to the minus a constant r to the 4? And if so, how is that constant depending on the shape? Okay, so this is an interesting question. So what kind of functional is it of the shape? If you are taking the Poisson process, it's always e to the minus the area. So that constant would be just the area of A. But here it cannot be the area. I mean, it doesn't make sense if you just see by scaling. It cannot be that area. It has to be something else. And Karthik Adhikari and Nandakishore did. So they were students, IISc graduated last year. So they considered this problem and they managed to find the constant. So if you look for any region, let's say you can scale it and assume it's inside the disk, probability there are no points inside the r times a large dilation does decay like e to the minus a constant times r to the 4. And that functional of shapes, what is that functional of shapes? It comes from some variational problem. It is the infimum of some functional on the space of measures. So you see some large deviation obviously here. What that is, I'll explain. So what is this infimum of what? This is this infimum is over all probability measures which do not put any mass on A. Okay, they are probability measures supported on the complement of A, and you minimize this integral mod square d mu of z minus double integral log mod z minus w d mu of z d mu of w. So if you do that, then that is exactly the constant. Okay. So in fact they show some things more interesting, which I should say that one of the things in large deviations is not only to ask for the probability of the large deviation, but suppose that happens, how does it happen? What is the way in which happens? So suppose that large deviation event happens, then how does the system look? So in this case, suppose you have a large square and you condition that there are no zeros inside. So what you see is, according to the result, all the zeros that should have been here, they kind of sit on the boundary. Okay, according to some measure, it's not uniform. It is a measure called balayage measure, but the points outside are completely unaffected. Okay, they look like the original ensemble, but the points inside, they just have to go to and arrange themselves on the boundary in a particular way. So this is how it will look when you condition on this large deviation event. Huh? Yeah, so that's actually, yeah, so the minimizer, the minimizing measure is basically something like that. It is uniform, I mean, well, okay, here I have to scale it and say it properly, but yes, it comes from the what is the minimizing measure, that's all, of this variational problem. Okay, so it is, yeah, so that's what it is. Actually, there is an even more interesting behavior for the Gaussian entire function zeros, which was recently, like again last year, done by Shubhashekhar Ghosh and Alan Nishri. You can consider the same question in the Gaussian entire function zeros. But there they are not able to do general shapes yet. They are only able to do it for the disk. Okay, so for the disk we already knew the whole probability. It is e to the minus that 3 square by 4 r to the 4 whatever. But suppose you condition that there are no zeros inside the disk of radius r in the Gaussian entire function. How does it look? All the zeros that should have been here, they will kind of sit here, okay, but then there is some region which is completely vacant, and then it starts looking like the original process. So there is no such vacant region here. So just everything sits on the boundary, and then the process is as usual. Whereas here there is this annulus, that some shield is created where there is no points actually. So it's a very interesting phenomenon. Again, it comes from some other large deviation, much more difficult.
Because if that annulus is also empty, then there is a bigger set.
Yeah, so there are, no, on the boundary, yeah, so yeah, there is that singular part of the measure, and then there is a shield. Yeah, so this means when I say this, really I should scale everything, and then this annulus size is of the same size as, it's of proportion to r. So it's not something vanishing when r goes to infinity. It's proportional to r. Yeah. Oh, with this measure, okay, I have to think really. The balayage measure is, how does it sit? Is it more, does anybody here know what a balayage measure is? So does it sit more on the corner or the, okay, sorry, I don't know, I have to think. So they actually compute it explicitly for several shapes in their paper, which I do not remember now. So as I already said, it's clear that this comes from a large deviation principle. So what is that large deviation principle from which it comes? Yeah. Yeah, it's the exact analog of it, but now it's in the complex plane. So what you are saying is exactly what comes if you look at eigenvalues of the GUE matrix that's on the line. This is exact analog of it. These eigenvalues are in the complex plane. Yeah, so that's exactly what I have in the next. See, if you look at the finite Ginibre ensemble, I had written in the first slide. Okay, so the finite Ginibre ensemble is n points, and Ginibre found the exact density of the eigenvalues. So that can be written as e to the minus summation mod zk square times the van der Waals square. That's what the density of eigenvalues looks like. But suppose those eigenvalues sit in a disk of radius square root of n. Suppose we scale everything by square root of n, then the density of points looks like this: e to the minus n square times summation mod zk square another type. So if there should be a 1 over n summation zk square. Okay, so in that expression it is 1 over n summation zk square, and then you have minus 1 over n square summation log mod zi minus zg. So it looks very much like integral mod z square d mu of z. I mean, if you look at the empirical measure of these points z1, z2, zn, then this is like the integral of mod z square d mu of z when you put the 1 over n, and this looks like the double integral of log mod z minus w. So it's exactly the same what happens in the one-dimensional GUE case. So this is the large deviation. So the rate is n square and the rate function is given by this. But this is for finite Ginibre ensembles. So I just end with remarks. So that's exactly what comes up. So it's motivated by that, and this kappa of A is coming from there, but it's not direct, at least not for us. If you want to be rigorous, then it strongly motivates but doesn't immediately prove the actual fact for the infinite Ginibre ensemble. There are a couple of things that one has to do. One is that one is what they did in their paper. They essentially showed that if you look at the infinite Ginibre ensemble and ask for the probability that there are no points in R times A, it's more or less the same as if I do with the finite Ginibre ensemble but with 2R square points. If you take a sufficiently large n, which depends on R like this, proportional to R square, then that finite Ginibre ensemble and the infinite Ginibre ensemble, they have roughly the same kind of probability there. And also another important point, which is actually, I mean, it may look silly, but whole probabilities are not given by large deviations in if you are strict about it. So because in large deviations there is a precise statement in terms of a topology, and when you have empirical distribution large deviations, you have usually topology of measures, and if you look at the event that there is a hole, that event in the space of measures, it has empty interior. So you don't get any information from the large deviation result. You have to usually go back to the proof and then rework the whole thing. Okay, but that's the essential point. And for the Gaussian entire function zeros, Ghosh and Nishri did a similar thing, but with a more complicated large deviation principle due to Zaituni and Zeldich for random polynomials. Okay, so that's all.
Why are the points not forming the annulus when you have a square and they are for the...
Oh, no. It's not the difference between square and the disk. It is the difference between the Ginibre and the Gaussian entire functions. In the case of Ginibre, even for the disk, okay, if I say the statement for the Ginibre, then for the disk, all the zeros will sit here and the Balayet measure will be just uniform measure here and the rest is business as usual.
Right.
For the Gaussian entire zeros, this is the case.
The other way around, you say the square and the Gaussian measure will have
No, it will probably have, but this has not been done for the square at all in the Gaussian entire function because nobody knows the constant. For example, you are doing conditional probability, you have to be very precise about the large division probability. If you don't have that constant there, then you cannot do this, at least this way of doing it. So in case of the Gaussian entire functions, one does not know the constant in the exponent for the square. One knows it for the disk by the work of Alan Nishri.
But can I understand this of these having a multiple interaction? That you would say in the example where you have this annulus, there's so much repulsion coming from all the particles on the boundary that it's pushing out.
It could be that. Actually, we don't understand the density of zeros of the polynomial that well in some sense. Yeah, but it is that is the case.
Like that.
Yes.
Okay.
So there is another related phenomenon, which is a very interesting phenomenon, which was found by Shubhashekhar Ghosh and Yuval Perez. So it is like this, which is a very related and important phenomenon, that if I mask a disk and you see all the points outside, what can you say about points inside? In case of the Ginibre ensemble, if you know all the outside points everywhere explicitly, then you can tell exactly how many points there are inside. So in some sense, you can subtract all the points and you can get the number inside. But you cannot say anything more. Whereas in case of the Gaussian entire function, if you know all the points outside, you can tell how many points are there inside and what is their center of mass. It's in some sense even more rigid, but you cannot say anything more than that.
So I missed it already. For this Gaussian ensemble, for long distance, is it still log repulsion?
No. It is not negatively correlated. Yeah. So for I wrote this P of ZW, and Z and W are close. They are like mod Z minus W square. That means it's kind of negatively correlated at short distances. But if you go far enough in the Gaussian entire function, there is even positive correlation. Well, very mild, but it is. So.
And the second question is, so this one is like a function in two variables, basically, right?
Which one?
It's Gaussian, this polynomial.
Oh, yeah, x and y.
But if I generate to three variables with some choice, can I get again a uniform kind of density?
Well, if you take three variables, you have to take, so see, this is it's actually two functions in two variables, the real part of the function and the imaginary part. If you want a discrete set, you have to take three functions in three variables. There are people who are studying power series, random power series in several variables. I have never looked into that. If you take just three variables, then you will get random some surfaces and other stuff like that. I don't know what good results are there about it. I don't know. Yeah, there are interesting things to do there, I think. I have not seen something like that. Yeah.
Zeros
outside?
Yes.
No inside. So if there is
No, not the positions. You know the number of points inside, and you know the center of mass.
No, but in the case of the GD.
Then you only know the number of points. You don't know the positions. Yeah.
So for the Ginibre, is anything known about for finite Ginibre, like for the outermost guy?
Oh yeah, it's easy. It will be Gumbel or something like that, because unlike in the case of there are so many different directions. You have in square root n, but you can have that extreme in any direction, and they are kind of independent. You may think so. You basically it's an easy calculation to do.